the structure of this is going to be pretty straightforward. I'm going to give a presentation which is an overview of Mass Motion, what it is, how we've gotten here, and what we've used it for. And then there will be a brief demonstration of the software running on a very simple scenario, and then we'll take questions. So, without any further ado, let's move in. So the first thing that you'll see is a video, which hopefully is coming through to everybody. If not, I believe that the video locations on YouTube have been forwarded for viewing either now or later. This is just a compilation of lots of different places that we've used Mass Motion, from rail stations to security, lobby design with elevators and security, streetscapes, including things like transit and crosswalks. Again, some large transit centers around the world have had their design process aided by Mass Motion. A fair bit of work in venues, venue design, and egress, and the video just sort of finishes up with some demonstrations of how the visualization of the simulations can be taken all the way to a really quite high level of detail. So, what is Mass Motion? Probably a few people have heard of it, but I do find there's a bit of stale information around the firm about what Mass Motion is and what it does. And I guess the interesting thing is that Mass Motion is certainly not the only pedestrian simulation software out there. Arup has and continues to use just about all the major packages that are available for use. But we discovered that the tools that existed in the market were not particularly good at integrating with the sort of design process that we engage in with our architect clients, but also when we work directly for sort of public transit authorities or airport authorities and this kind of thing. We wanted something that was going to fit in much better with sort of emerging practices of 3D design, the ability to communicate sort of to non-technical audiences with good visuals, and also the ability to scale our models to extremely high volumes and well beyond what else is available in the market. So, having said that, what is it that really makes Mass Motion different? Well, first of all, it is a fundamentally 3D application, whereas other products on the market are effectively 2D simulators that perhaps have a 3D sort of visualization bolt-on. Mass Motion does work exclusively in 3D, so that even relatively even flat scenes need to be constructed using 3D geometry. One of the advantages of this is that you can have sort of arbitrarily complex 3D environments, multi-level, quite large sizes, which have models which are kilometers by kilometers, multi-story, with tens of thousands of people in them, and this is the agents have the ability to navigate their way through these very complex environments on their own. Excuse me. The scalability and the ability to communicate through the 3D models has proven to be very powerful in a number of the projects that we've worked on, and the extent to which the models can be scaled. We've, as it says here, we have tested models of 350,000 simultaneous agents. That's not meant to be an upper limit. We actually don't know what the upper limit of simultaneous agents is in Mass Motion, but critically, the ability to scale to very large problems, but also to run smaller scale problems at a very rapid pace is a huge advantage when trying to answer problems on the fly and as they develop during the design process. Just stepping back a little bit and talking about the process of any simulation, Mass Motion certainly included, there is always the need to engage, with the client, whether they're a designer or an operator, what have you, and really come to terms with what the assumptions are, what the base data is, and how to how to go about constructing scenarios which are going to effectively answer questions. The process of data collection is not to be underestimated in this process, but once all of that has been settled, the application of a tool like MassMotion is a very powerful component in the design process. There is a requirement for there to be a 3D environment, as I said. That can be something which is either done by the architect by leveraging their models, or by the MassMotion team. And then moving through the sort of workflow, there is the simulation of specific scenarios, the analysis of various conditions, and then quite frequently it really turns into an iterative process where as results are analyzed, there may be problems which are exposed, or there may be design changes which are happening for other reasons which need to be sort of continuously fed back into the model. In slightly more detail, looking at the different steps of that process, 3D modeling is, again, something that can be done directly within the MassMotion workbench, but it can also come from various CAD programs. We've tested fairly extensively with AutoCAD, MicroStation, Revit, and Rhino. Once the 3D geometry is created or imported into the MassMotion workbench, the next step is to classify the various objects in a scene into things like floors, links, and links can be things like doors, stairways, escalators, and then portals, which are the entry and exit points for agents in the model. One of the really fantastic things about MassMotion in the overall design process is that because the root network within MassMotion is generated automatically based on the geometric arrangement of floors and links, it is very easy to make changes to the models just by changing the geometry. So there's not a need to rekey in roots or for the user to take time to develop things or input percentages of where agents are going to go. It all updates itself automatically just as you change the design geometry. One of the other big components of getting modeling right is that there are a series of sort of pre-simulation validation checks that are done for the user automatically to make sure that things are configured properly, that there is a floor at either end of a stair, for example, and that there are valid relationships between the objects in the scene and the way that the agents are meant to be interacting with them, which brings us to agent scheduling. Obviously, the agents need to be told when they're going to be coming into the scene and where they're going to be going, and that agent scheduling gets tied to the portal objects within the scenario. MassMotion can handle extremely complicated origin and destination matrices. There's no real limit to that. The origin and destination matrices can be defined either through the workbench or through spreadsheets, which is a not uncommon way of organizing things in the transport planning market anyway. The agents themselves can be organized according to various profiles, or according to multiple profiles where you might have different sizes or speed profiles or characteristics that you want the agents to have throughout their existence in the scene. And that can include things like coloring the agents such that you can tell different user groups apart in a scenario. Once the environment and the agent scheduling are set up, the next step is obviously the simulation. And really what happens during simulation is that there's a series of initial algorithms which are run, which go through and make all the connections between floors and links and generate the routes that the agents will be able to perceive as they're moving through the environment. On that basis, the agents enter the scenario according to their schedule, knowing where they're meant to be going, and the they are able to make their way on their own from their origin to their destination. And they make determinations about things like overall route distance, the amount of congestion that's apparent to them in any given location, the amount of vertical transition that a given route might have, and they make their own decisions based on sort of unique personality profiles per agent, and they even have the ability, as the scenario evolves, to make changes. So if they make a decision and then determine that in the process of getting to a door or a stair or something, a certain amount of congestion has developed, they can reevaluate their route and in fact choose alternate routes where appropriate. And then the other thing, which is quite important for the process of doing technical analysis work, is that quite a lot of data is collected during the simulation process. In addition to capturing statistical metrics such as queue length, flow rates on various areas, populations, the entire simulation can be recorded in 3D such that at every frame the position and various characteristics of each agent is captured and recorded for review and analysis. So that brings us along to analysis. This ability to record the entire simulation in 3D and play it back is hugely valuable. First of all, for the mass motion user to be able to visually verify that the model is running in an appropriate way. But it can also be incredibly valuable for communicating and collaborating with the rest of a design team. I've personally had experience where after running a model, we'll just sort of load the recorded simulation results on a laptop and take it to a sort of multidisciplinary design review and go through all the issues. Is there congestion here? Do we need more vertical circulation here? And it just, the ability to move around a 3D model that has pedestrians moving around in it in real time is just a hugely hugely valuable tool in terms of being able to communicate problems and to be able to engage people from all various disciplines in the issues at hand. In addition to the visual verification and review, there is the ability to review the statistical output from the model. There's also the ability to use the recorded data to generate new types of data, such as density maps or coordinate counts at particular locations that weren't designated during the simulation, and then this information can be exported and used in reports or graphed and that sort of thing. Talking a little bit about calibration and validation, there is, for the sake of the discussion, we define calibration as the tuning of variables to established sort of metrics or research. So, for example, the default behavior of the pedestrians in a mass motion simulation is to conform to the speed density profiles that were developed by John Fruin, and which form the basis for virtually all of the sort of standards that are applied around the world by various agencies. And it has to do with the rates that people travel at, the speed profiles that they use, and the number of people that can fit through openings in various different conditions. The validation side of things we define as how well a mass motion model is able to replicate observed real-world behavior. So when we do original surveys on say the way that agents choose their exits from a complicated train station, or the overall journey times for agents getting out of a building in an evacuation scenario, that's what we mean by validation. And we've been able to demonstrate extremely good levels of conformance in both the sort of route choices that the agents make and the and characteristics such as overall journey times in egress models. So we're quite confident that Mass Motion is very well calibrated to sort of establish knowledge in the area of pedestrian planning, and that it's been validated well against a series of test cases. I think one of the real strengths of Mass Motion from an Arup point of view is that it is a tool that we have direct control over, and that we are able to leverage for various disciplines and approaches. This is an example of mapping the, I'll just run that again, mapping the intensity or frequency of vision in one of the BART stations in San Francisco. And this is, I think, certainly people we've talked to in the retail industry that are quite interested in this, the idea that you might be able to reevaluate or negotiate rents or that sort of thing, or place advertising based on where people are going to be looking. I think it also has some implications about where walls ought to be in the first place. Certainly if people are looking at the corner all the time, maybe that corner ought not to be there. There's also things that we've begun experimenting with, integration of CFD for smoke and fire data. There is the compatibility with Arup's real-time software, Submerge, and multiple agent types, like for instance including bicycles in pedestrian simulations. Talking a little more specifically about where we've applied Mass Motion, quite a lot of the work has been done in transportation planning and terminal design. A number of large stations around the world, Union Station in Toronto and Transbay Terminal are ones that I've had significant personal experience with, but it's also been used by teams in Australia on the Sydney CBD Metro, a bunch of the subway extension work here in Toronto, and a couple of airports, JetBlue Terminal in New York and Trudeau Airport in Montreal. For fire and evacuation, there's been a number of sort of both validation studies and actual application of Mass Motion to various scenarios. Here is the Canary Wharf validation exercise and some TTC subway station evacuations as part of the upgrade to their fire and to their tunnel ventilation system. Also done excuse me, a fair bit of venue planning work. The Air Canada Centre is a big sort of major league hockey and basketball facility, and then a number of explorations of sort of smaller venues as well, performance spaces. Talking a little bit about some of these case studies in particular, just to give a feel for the scope of the work that's been done. Union Station is one that I do have a lot of experience with, and this project is interesting because the volumes of people are quite extreme. Something like 35,000 people in the peak 15 minutes in some of the models. It's a very busy station. It is the hub of the entire city of Toronto's regional rail system. And they're undergoing a complete revitalization of the station. A Mass Motion has been applied to understand whether the final design is going to be appropriate, and there's been significant input from the models into the development of the design, but also into the development of construction phasing planning, which, as the station has to remain operational for the entire period, that's no small task. And being able to understand how closures of concourses and routes is going to affect the overall flow of people has been hugely valuable for the owners and the operators alike in understanding what can be done as part of the design, but also what needs to be done as part of their operations to make this a successful project. Transbay Terminal in San Francisco, another big multimodal facility. A lot of bus activity on an upper deck, and significant regional rail and eventually high-speed rail activity in the basement of this building, and then to a ground floor concourse and an underground passenger waiting mezzanine. A lot of interesting connectivity to the neighborhood issues, a lot of interchange between the various services. It's and really a very very complex system of vertical connections between the various levels, and this is a project where, as I said earlier, the ability to take results in and talk to a design team about issues relating to the design or planned operations has just been hugely useful to understanding what the issues are and what needs to be done about them. Talking a little bit about some airports work, at JetBlue, it was an interesting study because we were looking really at the impact of retail activity on general passenger circulation, because the Port Authority of New York and New Jersey was concerned that if they ever inherited the terminal, that they would be able to use it as they saw fit, and we were able, through the use of mass motion, to demonstrate that the layout would support basically unhindered movement of arriving, departing, and transferring passengers. Looking at the example of Trudeau Airport in Montreal, this is a more traditional airport operation simulation where we're actually taking a look at, as this video shows, the international departures area. So this is kiosks, traditional check-in and bag drop operations. There is another piece of work that was done subsequent to this, which was looking at the security configurations that were planned for both the international and domestic operations. And I think, again, this was, from the client's point of view, this was really useful to be able to show the results of a simulation in 3D to their clients, which are the airlines, and to be able to convince them that you know, there was a good use of investment money and the airlines' landing fees in the development of the new departures concourse. A little bit on venues. This is just a demonstration of some work that was done as part of a design competition for a theater in Germany, Bonn, I believe. And really, there were some questions that came back from the competition panel about, okay, well, how is the facility going to work in terms of the public space, sort of before, after, and during intermission times, and we were able to use mass motion to convince them that the design was going to be very effective in terms of patron movement, but also, you know, sort of patron circulation and waiting during intermission times. It gets us around to, you know, where is the value in using mass motion? You know, it has been designed to be an effective and well integrated part of the design process, and sort of well in excess of the competition in the marketplace. And you know, the real benefit of having something like mass motion and its predictive abilities is that it eliminates, or at least it enables, the management of risk in designing these facilities or managing, you know, the change in operations of facilities. The ability to communicate the design concepts and how people are going to fit in them is also a very powerful thing. And then, you know, when it comes to dealing with you know, jurisdictions having authority and the like, and being able to demonstrate, you know, either code conformance or sort of a performance, the effectiveness of a performance-based design approach, you know, the statistical outputs are very useful for those discussions. And it you know, due to its 3D nature and the way that it's been designed to work, it you know, it integrates quite well with other design tools that we're used to using in the market, whether it's CAD or the emerging sort of BIM approaches with Revit and the like. And that, I think, brings us pretty much to the end of the presentation. And I'm just going to step out of this and move into just a brief demonstration of the mass motion interface and how it works. You should see on the screen a relatively simple layout. We've got 5 floors connected by a number of links which might represent doorways or what have you, and really all we're going to be doing is we've got one portal here which is going to be where the agents are going to come from. We've got another portal over here which is where they'll be going, and in between we also you'll note that there's a couple of sort of hollow boxes here which indicate that there's some gate control on these links, and what that should do is just sort of cycle the opening and closing of these on and off. And what I am going to do is just export all of that. And open up the Mass Motion Simulator. And we'll run it. And you'll note that the gates start closed, so you can see they start red and go green and open up. The other thing you'll notice is that as queuing builds up for this link, the agents will sort of automatically start diverting around to the alternate route. You can see that they basically have at least as efficient a route doing that divergence as they do waiting for the queue here. And now you can see that the gates are cycling on and off, and that the number of the people are being held up in this room or not, depending on the number of people. You also note that the way that the agents are entering the scene is actually spread out across the floor that the portal is on. It's possible to either have the agent spawn directly on the portal or on the floor associated with it. And I think that's all the population that's going to run through this model. So if we stop it, we can also go back now that we've run this simulation, turn on the analysis component, and we can see here the playback of the simulation. It's worth noting that it's possible, in fact, to start reviewing a simulation even in advance of the simulation completing. So that can be quite useful, especially if you're running a very large model. You may have noted, although I went through it very quickly, that when you open a project, you have the ability to either run it with the 3D viewer on or off. It is faster to run it with the viewer off because the graphics card can become a bottleneck for the simulation. And if you run it with the viewer off, you can still look at the results if you're recording them just by observing the recorded information here. One of the other things that you'll note is that there's a series of sort of analysis objects that have been put down here, which sort of start demonstrating the various types of density that can be recorded. This, I believe, is just a sort of time average density using the level passageway standard. This is a similar thing, except that it uses the queuing standard, which requires much higher densities to begin coloring the floor. This is maximum density. I forget what this one is actually. This one is instantaneous density. So this is kind of is almost like a sort of ant trail approach to things. I think this is also just we can check. What is it? Experienced average. So this is over time it records the average density, but only when there are people there. So this is useful when you have something like a railway station where you have periods of very intense busyness and periods of not much activity at all, and you want to know what the passenger experience is. So information is really only stored here when there are people there.